Prior to this lesson on transformation of functions, you should have had some experience in graphing equations by the point plotting technique, where you just at random choose a value of x and find the corresponding y value, and then by locating enough of these points you get an idea of the sketch of the graph. The other things that you need to be familiar with are the concepts of symmetry, intercepts, what a function is, and what the domain and range of a function means. And also you should have had some experience with certain basic functions like the square function, the cube function, the absolute value function, the square root function, and some others. If you've had that background, then you're ready to do this lesson, which concerns how you can take the knowledge that you have gained up to this point and use that along with some new concepts that we'll see in this lesson to make graphing certain equations much easier for you. I want us to take a look at a couple of graphs first of all, just to get you into an idea of how you can determine by looking at the equation of a function perhaps what's going to happen to that graph. We are to sketch the graph of each of these functions given here. In our first function, part A, our function reads f of x is equal x squared plus 2. Now you should be familiar already, if I cover up that plus 2 right there, with the function f of x equals x squared. You should have what I call a mental picture of that graph. You may recall that f of x equals x squared forms a graph that we refer to as being a parabola. And it has a vertex at the origin, and it has some symmetry with respect to the y-axis. What we're going to explore here is what effect does that plus 2 in the equation have on our graph of y equals x squared. So I think what I'm going to do here is just a little bit of point plotting, and we'll do this rather quickly. If we choose x to be 0, you can see that 0 plus 2 gives us a y value of 2, so I'm going to locate that 0, 2 point here on my graph. If x is 1, 1 squared plus 2, 1 plus 2 would be 3, so whenever x is 1, y is 3. If we choose x to be 2, 2 squared is 4, 4 plus 2 is 6, isn't it? So 2 gives us a y value of 6. Notice if we choose x to be negative 1, if we square negative 1, we get positive 1. 1 plus 2 is 3. So whenever x is negative 1, I get 3. And if x is negative 2, what's going to happen here? If we square negative 2, we get 4. Plus 2 is 6. So when x is negative 2, we get 6. And you can see from these points that I have located, my graph is still a parabola. But what has happened to that parabola? Instead of the vertex being down here at 0, 0 and opening up, our parabola has moved up. And how many units has it moved up? It's moved up these 2 units that was added to our function. Now, if you think about what this equation is saying, that makes perfect sense. Because what we're saying is we're taking the y values we would get when we square x, and what are we doing to those y values? We're adding 2. So what that will do is move all of our points up 2 units from our original graph of y equals x squared. On our second graph, notice our function is f of x equals x squared minus 4. You may already have an idea of what that minus 4 is going to do to our graph of y equals x squared, but let's see what happens when we choose points. If x is 0, 0 subtract 4 is negative 4. So I'll locate 0, negative 4. Whenever x is 1, 1 squared is 1, 1 minus 4 is negative 3. So I will locate 1, negative 3. Notice when x is 2, 2 squared is 4, 4 subtract 4 is 0. So I have the point 2, 0. I could go on with other positive values, but let's get some negative numbers here. If x is negative 1, negative 1 squared is 1, 1 minus 4 is negative 3. So negative 1 gives us negative 3. And notice if x is negative 2, if I square negative 2, I have 4. 4 subtract 4 is 0. So x equals negative 2 gives me a y value of 0. And again, you can see our graph is that same y equals x squared parabola that has done what? it has been moved down. How many units? 4 units. So instead of our vertex being at the origin, that vertex has been moved down 4 units. Now what we're going to do then is look at a rule that explains whenever we have a number either added or subtracted from a basic function that we already know the graph of, basically we can know what that graph's going to do. It's going to look like the graph of our basic function, but it will have been translated either up or down from its original position. Let's look at that statement. Vertical shifts of graphs. Notice it says if C is a positive real number, then the graph of y equals f of x plus c is the graph of y equals f of x shifted vertically upward c units. Now this function could be anything. In our last example that was the square function, y equals x squared, or f of x equals x squared. And we saw when we added a number to that, it just moved that graph up. If c is a positive real number, then the graph, oops, there's a misspelling here, isn't there? Graph, G-R-A-P-H. The graph of y equals f of x minus c is the graph of y equals f of x shifted vertically downward c units. Again, this function could be any function, but what we're seeing is if we show a subtract some positive number, then that minus c is going to move our graph downward. If you have good mental pictures of those basic functions that you learned earlier, like the square function, and you know that parabola's shape, then you can easily graph a function that has been translated vertically upward or downward just by moving that shape up or down, however many units is concerned. Let's look at another example. Sketch the graph of each of these functions. Now I want you to notice in these equations, they're a little bit different than the ones that we looked at earlier. I'm going to slide this back up here on the screen so you can compare. Notice here we have x squared and then we're adding 2. Notice in this function we're adding something to x first. It's in the parentheses, so we're adding to x first before we square. So that's the difference. Here we're squaring first and then adding. There's a big difference in what happens to our graph, as you will see. Again, we're going to do this just by picking some values of x, and then we're going to discover what happens. If I choose x to be 0, 0 plus 3, of course, is 3, and when we square 3, we get 9. So whenever x is 0, my function value, y, is 9. Okay, that's 7, so I'm going to approximate about 9 right in there. Now I want you to notice right away, if I take a positive value of x and I add 3, like 1 plus 3, that's 4. When I square 4, I'm going to get 16. Those answers are going to be very big, and they're going to be off my graph here. So I'm not going to use any more positive values of x here. Let me choose a negative value, and let's see what happens. If x is negative 1, negative 1 plus 3 is 2. When I square 2, I get 4. So whenever x is negative 1, I'm getting 4. Notice when x is negative 2, negative 2 plus 3 is 1. What do you get when you square 1? You get 1, don't you? So x equals negative 2 gives us a y value of 1. Do you see what's going to occur whenever x is negative 3? Negative 3 plus 3 would be 0. If I square 0, I have 0. So negative 3 gives me 0. Let's go to negative 4. Negative 4 plus 3 is negative 1. If I square negative 1, I get positive 1. So whenever x is negative 4, I get positive 1. Negative 5 plus 3 is negative 2. If I square negative 2, I get 4. So whenever x is negative 5, I have 4. And I think you can see, again, our parabola is taking shape here. But what has happened to our parabola in comparison to our graph of y equals x squared? Y equals x squared would have our vertex here at the origin, wouldn't it? Be opening up from here. Our graph, notice, has been shifted to the left. Okay? It's been shifted to the left. Adding 3 to x before I squared moved my graph 3 units to the left. Now, let's look at this one, and we're going to generalize. Notice again, we have something happening to x before we square. Notice here, whenever x is 0, 0 minus 1 is negative 1. When I square negative 1, I get 1. So 0 gives me 1. Whenever x is 1, 1 minus 1 is 0. When I square 0, I get 0. So 1 gives me 0. Whenever x is 2, 2 minus 1 is 1. When I square 1, I get 1. So 2 gives me 1. 3 minus 1 is 2. 2 squared is 4. So whenever x is 3, I'm getting 4. Let me go back over here and show you about negative 1. Negative 1 minus 1 is negative 2. When you square negative 2, you get 4. So when x is negative 1, we have 4. And again, you see our parabola taking shape, our y equals x squared shape here. But what's happened this time? Our vertex has done what? It has moved to the right 1 unit. So subtracting 1 from x before we squared had the effect of moving our graph to the right. Now, I want to put this back up here and let's do some comparison. When we had a number added to our function, in other words, the square happened first here, when we added to that, our graph moved up. Now that's sort of natural because we think of adding and on the y-axis going up. Here, when we subtracted, we moved down. Now, in this situation, it's sort of backwards to what we expect. Notice when we added 3, we didn't move in the positive direction on the x-axis, but rather we moved to the left. And when we subtracted from x, we moved to the right. Now, here's what I like to do sometimes to help me with this. If I have a quantity like this with something happening to it, in other words, something is occurring to x before I do whatever the function tells me to do, what I can do is I can say x plus 3 equals 0, x equals negative 3. This tells me that what used to happen at 0 is now occurring at x equals negative 3 because negative 3 makes this value become 0. So what used to happen at 0 is now happening at negative 3. Okay? Now notice how that works here. If I take my x minus 1 and I set it equal to 0 and I solve for x, notice that what used to happen at 0 is now happening where? At x equals 1. So however you choose to remember this, this is important. Let's look at our rule that we have concerning this translation. We call this a horizontal shift. If c is a positive real number, then the graph of y equals f of the quantity x plus c is the graph of y equals f of x shifted horizontally to the left c units. Now this is really important that you understand. In this parenthesis is x plus c. Our argument of our function is now x plus c instead of x like the original. So when the argument of our function is changed, if we have plus a number on the x, we're moving to the left. Okay? Here, if c is a positive real number, and that happened again, if the graph of y equals f of x minus c is the graph of y equals f of x shifted horizontally to the right c units. So again, notice the argument of our function is now x minus c, whereas it used to be just x. If we're subtracting from x, then our graph moves to the right. At this point, we have talked about both vertical translations and horizontal translations, or shifts if you prefer using that word. And the difference, remember, is whether we're adding or subtracting to the function value or whether we're adding or subtracting to x before we perform that operation that the function implies is to be performed. You'll want to spend some time with those and be sure that you understand those concepts of translations. The other part that we want to look at in this lesson is to also talk about reflections and compressions or stretches. Now we're going to look at reflections in this next example. I want you to think about the idea of when you tested for symmetry. Remember, to test for symmetry, to test for the y-axis symmetry, you would change x to negative x, And what that implied was that what was happening on the right-hand side of our y-axis would be sort of repeated or a mirror image on the left-hand side. To test for symmetry to the x-axis, remember that you replaced y with negative y. I wanted to review those concepts because I think that may help you a little bit when you think about these reflections. This says to sketch the graph of each of these functions. In part A, our function is f of x is equal to the negative square root of x. Okay? So again, I want you to think about if that negative sign were not there. If we just had y equals the square root of x or f of x equals the square root of x. Do you recall what that graph looked like? Now, for most people, this is not quite as familiar as the y equals x squared graph is. So what I'm going to do down here is just to remind you, if you have an xy axis, that the square root function has a graph that looks sort of like that. It looks sort of like half of a parabola. 0, it goes through 1, 1, it goes through 4, 2, and so forth. And of course, that's without that negative sign in front of it. This would be the graph of y equals just the square root of x. And you should be familiar with that graph and have that picture. Now, I want us to look at this equation and let's think about what's going to occur because of that negative sign that we have in our equation right here. Notice we're going to perform the square root first, and then we're going to apply the negative. So what does that tell me about my y value answers? My y values are going to be negative, aren't they? Notice if x is 0, the square root of 0 is 0, and minus 0 is still 0. So we still have our point at the origin. But notice whenever x is 1, we're looking for the negative square root of 1, which would be negative 1. Whenever x is 4, we're looking for the negative square root of 4, which would be negative 2. And if you continue with some other points, what you're going to have is this graph right here. Now, I want you to compare these, the shapes. This graph and this graph are reflections of each other in the x-axis. In other words, if I took this graph right here and I reflected it in the x-axis, I would have a mirror image down here, wouldn't I? And that is exactly what this graph looks like. Now, I want to show you with this equation, and I'm going to rewrite it with a y instead of an f of x here for a second. If I have y equals minus the square root of x, I could multiply both sides of this equation by negative 1, and that would give me negative y equals positive square root of x, right? Well, notice how this equation right here compares to this one up here. What's happened? Y has been replaced with negative y. And when you replace y with negative y, that's that test for symmetry to the x-axis, isn't it? And so what that may help you to do is when you see an equation where you've got a negative in there, if that negative could be placed so that it really is associated with the y, that tells you that you're going to have a reflection over the x-axis because you're changing your y values to negative y's. Okay? Now, let's compare that to this problem. F of x is equal to the square root of negative x. Notice here our negative sign is inside the square root. That means we're going to apply the negative to x first before we do the square root. And now that's different than here, isn't it? Now, we're going to have to be careful here. In fact, you may be thinking, you can't do that because you can't take a square root of a negative. But don't forget, we can choose x values that are negative. And so I'm going to, just for emphasis on this one, because it is a little bit tricky, I'm going to do a little table. What if x is negative 1? What is minus x? Okay? If x equals negative 1, then minus x is positive 1, isn't it? So if x is negative 1, then minus x is positive 1, and notice this is asking for the principal or positive square root of 1. So I'm going to get a y value of 1. So whenever x is negative 1, y is positive 1. Notice if x is negative 4, minus x is going to be positive 4, and I'm looking for the principal or positive square root of 4, which is 2. So whenever x is negative 4, y is 2. I want you to also notice, of course, if x is 0, minus x is still 0, and the square root of 0 is 0. Again, if you get a few more points, you can finish out a little bit more of this graph, but I want you to notice this graph looks like that. Now compare the original y equals square root of x with this graph. How do they compare? Actually, this graph was what? It was just reflected over the y-axis. If you took this graph and did a mirror image over the y-axis, wouldn't you get this graph? Notice here, x has been replaced with negative x. X with negative x is going to reflect you over that y-axis. Let's look at our rule. Reflecting graphs. The graph of y equals minus f of x is the graph of y equals f of x reflected in the x-axis. Now notice here, y equals, and your negative is outside the function. In other words, you do the function first, and then you apply the negative. In that case, remember, here we could multiply both sides by a -1, and we could get negative y equals f of x. And so y has been changed to negative y. If you change y values to negatives, then you reflect over the x-axis. Okay? Now, check this one out. The graph of y equals f of negative x. Notice here, our negative is not in front of the function, but it's on the x. Y equals f of negative x. This graph is the graph of y equals f of x reflected in the y-axis. Notice here, x has been changed to negative x. X to negative x reflects you over that y-axis. Okay? Now, there's one other concept that I want us to talk about, and that is in terms of what happens when we have a number multiplied times something. Let's look at this. Sketch the graph of f of x equals 2 times x squared. Now notice here, you're going to square x, and then you're going to multiply by 2. Now let's think about it. If that 2 wasn't there, we know what y equals x squared looks like, don't we? But what is this 2 going to do? It's going to take our original y values and multiply them by 2. Let's get some points here. If x is 0, 0 squared is 0. 2 times 0 is 0. So whenever x is 0, so is y. If x is 1, 1 squared is 1. 1 times 2 is 2. So whenever x is 1, y is 2. Notice here also, if x is -1, what's going to happen? -1 squared is 1 times 2 is a 2. So we have this point. If x is 2, 2 squared is 4 times 2 is 8. That's going to be about right in there. And notice if x is -2, if you square -2, you get 4 times 2 is 8 also. Now, I'm going to put this graph on here, and then what I'm going to do so we can sort of compare these is I'm going to graph y equals x squared. Notice here, if x is 0, so is y. I have the same point right there. But whenever x is 1, y is 1. My point is down here. -1 would also give me 1. When x is 2, y is 4. Now, my y equals x squared graph, if you notice, is a little bit fatter than my y equals 2x squared graph. Notice it has the same vertex, so this has not been translated either up or down or left or right. It has not been reflected. All that's happened here is that our graph has sort of been stretched upward. It's become skinnier because of that stretching. And the stretching occurs because we're taking our original y values and we're doubling them. We're making them 2 times that. And so that stretches our graph up like that. Now, let's see the effect of this 1/2. And you might already have an idea of what's going to happen here. Notice if x is 0, 1/2 times 0 is still 0. If x is 1, 1 squared is 1. 1/2 times 1 is 1/2. Notice -1 would also give you 1/2, wouldn't it? If x is 2, 2 squared is 4. What's 1/2 times 4? 1/2 times 4 is 2, isn't it? So whenever x is 2, so is y. -2 would do the same thing. Here's my graph, and it would continue upward. Now, where's my y equal x squared graph? 0, 0, 1, 1, 2, 4. So there is the original y equals x squared. What happened when I multiplied by 1/2? Notice my graph is fatter. It's not opening up quite as fast as the original y equals x squared. We call that a compression. The graph has sort of been squashed down, if you will. Notice again, it has not been moved up, down, left, right, or reflected. It has simply changed its shape a little bit. It's been pushed down, made a little bit fatter because of that 1/2. And of course the key here is what we're multiplying by, isn't it? You might expect if we're multiplying by 2 or 3 or 4, that's going to make those y values get big faster. So we're going to have that stretching idea. If we multiply by a fraction, that's going to have our y values not get big as fast. It's going to slow that growth down, and so our graph will be compressed a little bit. And we see that written in our next rule here. Stretching and compressing of graphs. Notice here, if a is larger than 1, like that 2 a while ago, the graph of y equals a times f of x is a vertically stretched version of the graph of y equals f of x. We just stretched it up. If a is a number between 0 and 1, like a fraction, the graph of y equals a times f of x is a vertically compressed version of the graph of y equals f of x. Remember, those values were just sort of squashed downward, if that's not very good English, but it gives an idea of what we're talking about. Okay? Now, we're not really going to do very many of these probably in college algebra, but this sometimes also happens. If the argument of a function is multiplied by a positive number a, in other words, argument, we're talking about x, right? The graph of y equals f times ax, notice the difference between here and here. The a is times x first, and then we apply the function. That will be horizontally stretched or compressed instead of vertically stretched or compressed. A lot of times with these types of functions, you may want to just get a few values and sort of get an idea about what the shape of that graph is going to look like. Now, at this point, we have looked at sort of the concepts in this lesson. How can you look at an equation and know if it's going to be shifted vertically upward or downward? Do you have sort of a basic function with a number added or subtracted at the end? How can you know if your graph is going to shift left or right? In those cases, you have a number added or subtracted to x first before the operation of the function occurs. A reflection occurs when either a negative is introduced that could be associated with either y or x. If the negative can be associated with y, we're going to be reflecting over the x-axis. If the negative is associated with x, then we're going to be reflecting over the y-axis. And then finally, if we have a number multiplied times a basic function, that's going to stretch our graph vertically upward or compress it vertically downward. If we have a number times x first before we apply the function, that's going to cause a stretch or a compression in a horizontal direction. Now what we're going to do is to see how we can apply these ideas that we've looked at into some examples. Now here it says, given the graph of y equals f of x, draw the graph of y equals f of x plus 3. Now you'll notice here that we're not given an equation. So we don't have a mental picture, but we do have a picture here in terms of a graph. And these are definite endpoints. Our graph doesn't extend beyond these points. Notice here, the original function is here. After we've done the function, what are we doing? We're adding 3. So what does that do to your graph? It moves it vertically upward 3 units. Now the best way to sketch the graph then of this new function right here is to take specific points that we know here and move those specific points up 3 units, and then we can sort of mimic the shape of the graph. Let's start with this point right here. My x value is -3, my y value is -3. Now if I move that point up 3 units, I'm going to be on the x-axis, aren't I? I'm going to be at -3, 0. So I'm going to put a dot right there for that point. Now let's look at this point right here. X is -2, y is 1. What happens if I move that point up 3 units? My x is going to stay -2, but my y value is going to become 4, isn't it? So over here I'm going to go to -2, 1, 2, 3, 4. Okay? Now I'm going to go ahead and complete that part of my graph. Notice it's just a line connecting those points right there. So I'm going to connect those points right there. Okay? Now this should be easy This point, 0, 1, if I move it up 3, is going to be at 0, 4. And we have that horizontal line coming across like that. Okay. Now let's go to this point. The coordinates, my x-coordinate is 2, and my y-coordinate is 4. If I move that up 3 units, it's going to be up here on 7. So whenever x is 2, y is 7. And notice again, that's just a line up to that point right there. And then my final point, 1, 2, 3, my x value is 4, my y value is 2. If I move that up 3 units, my y value is going to be 5. So whenever x is 4, 1, 2, 3, 4, 2, 3, 4, 5, my y value is going to be here. And again, connecting those points. And you can see I've got just a mimic of my original graph, but that graph has been just moved up 3 units. And so that's the whole idea in our lesson. If you know the graph of a function, if you have something added, just move that graph up 3. Notice, remember, if that said minus 3, what would have happened? We would just move that graph down 3 units. Okay, now let's keep that in mind, and let's look at this one. Given the graph of y equals f of x right here, draw the graph of y equals f of x plus 3. Okay? Now here notice our 3 is being added to x first. It's added to the argument of our function, not after we do the function. Again, I want to emphasize the difference in notation. See here, the argument stayed x. After we did the function, we added 3. Here we're adding 3 to x first, then applying that function. Now remember, this causes not a vertical shift, but a horizontal shift. And what I like to do here is to think, okay, my argument is x plus 3. I'm going to set that equal to 0 and solve for x. So what used to happen at 0 now occurs at negative 3. Now here's 0. So what used to happen here is going to go over 3 units this way. So instead of being at the origin, I'm going to be over 3 units. Okay? Now that tells me right now what's happening to this graph. All of my points are going to shift to the left 3 units. So let's take this point right here. X is negative 3, y is 4. If I shift to the left 3 units, notice my x value is going to change to negative 3. My y value, I'm sorry, negative 6. My y value is going to stay at 4. And this point right here, my x value is 4. My y value is 4. If I move that 3 units to the left, I'm sorry, my x value is 3. My y value is 4. If I move that to the left 3 units, that's going to be an x value of 0. 0, 1, 2, 3, 4. Okay? And I'm just going to use those points and sketch in my graph. So it's this graph, move to the left 3 units. Okay? Let's do one more similar to this idea. Given the graph of y equals f of x below, draw the graph of y equals minus f of x plus 3. Now, this one has 2 things going on at once. What's this x plus 3 going to do? Well, if you set x plus 3 equal to 0 and solve for x, that says what? We're going to shift left 3 units, right? Now, what about this negative? Is the negative on x? No, it's not inside there. In fact, I could multiply both sides by a negative and get negative y equals f of x plus 3. So that's like changing y to negative y, isn't it? Remember, if you change y to negative y, you're reflecting over the x-axis. So we want to reflect over the x-axis. Okay? Now, let's see if we can picture what we're going to do here. If I reflect this over the x-axis, do a mirror image, I'm just going to sort of do that right here with some dotted lines. That point would be 2 units down here. This would be 3 units down. 1, 2, 3, 4. 1, 2, 3, 4. Okay. Now, this is going up like that. So this way, if I reflect it over, it's going to look something like that. And then it changes shape and it's something like that. This part is my reflection. Okay, there's my reflection. Now what do I want to do? Shift it left. So I'm going to take this point 3 units to the left. I'm going to be at 0, negative 3. I'm going to take this point right here and move it 3 units to the left. So that's going to be at -1, -2. Okay? Now let's go ahead and connect between those two. Right there. Okay? This point right here, I'm going to shift to the left 1, 2, 3 units. So I'm going to be at x equals 2, y equals -4. And then notice that part of the graph was shaped like that, so I'm going to do this. So this graph right here has this graph reflected over the x-axis and then shifted left. Okay? So sometimes it helps to draw sort of this intermediate picture in here to help you get an idea. Reflect over x-axis, see what that looks like, and then shift to the left 3 units, and then you have your sketch. Okay? Now, I want us to move from here where we had an actual picture to go by to go to an equation. And so what I want us to do is we look at the equation that we're asked to graph. We're going to analyze what's happened to this equation. Can I identify a basic function here where some little something has been changed? And if I can, I'm going to think about my mental picture of that graph of that basic function, and then what has occurred. Do I have a shift? Do I have a reflection? Do I have a compression or a stretch or whatever? And then we'll use that to help us get a real quick sketch of our graph. Sketch the graph of the given equation by applying transformations to a standard graph. My equation says y equals x cubed plus 1. Now notice here the cube happens to x first, and then we're adding 1. So this is like the cube function, and the plus 1 is going to do what to that cube function? It's going to move it up 1 unit. Okay? Now, if you've forgotten, over here I'm going to do what I call my mental picture of my cube function. My mental picture looks like that. Do you recall that cube function, y equals x cubed? In particular, there are certain points that I remember. The 0, 0, the 1, 1, and the -1, -1. Of course, also there's 2, 8, if you want to remember 2, 8, and -2, -8. Those are sort of key points on my y equals x cubed. All I need to do is just move those points up 1. So instead of being at 0, 0, I'm going to be at 0, 1. Instead of being at 1, 1, I'm going to be at 1, 2. And 2, 8 is going to become 2, 9. 4, 7, 8, 9. That's going to be up there. That moves up 1, so -1 is going to be on 0, and -2 is going to be at -7. And then see how quickly I have my graph. Okay? So it's just this mental picture. We know we're just going to do what? Move up 1 unit. And we've got a quick sketch. Okay? This says also to sketch the graph of the given equation by applying transformations to a standard graph. Now look at your equation. Y equals the absolute value of x minus 2. Now I recall an absolute value function, but notice here I'm doing something to x before the absolute value. Okay? So this is going to cause a horizontal shift. My basic function is y equals absolute value of x. Do you remember that basic graph? You should be picturing a V-shaped graph like that. It goes through 1, 1, 2, 2, -1, 1, -2, 2, and so forth. Those lines coming together to V shape. Now remember, when you have something happen to x, it causes a horizontal shift. And how do we decide? If x minus 2 equals 0, then x equals 2. So what does that cause me to do? What used to happen at 0 now happens at 2. So I'm going to go over here to x equals 2. And then I know that I'm just going to have the vertical line, or I'm sorry, not vertical line, the lines up from that point forming that V shape. And I have the sketch of my graph. Now you'll notice once I moved over to this x equals 2 point, I just went over 1, up 1. That's like 1, 1, 2, 2. So I can just do that same thing from this new point right here, can't I? Quick sketch. Of course, if you don't know what y equals absolute value of x looks like, then you can't do this that quickly. It's very important that you know these basic graphs. Sketch the graph of the given equation by applying transformations to a standard graph. Now, be careful on this one. It's very important that you understand what this equation is saying to you. When you have a negative in front here with a variable and with an exponent, You have to remember this is basically like saying -1 times x cubed, and your exponent happens first. This is not saying the quantity -x raised to the third power. Y equals quantity -x raised to the third power is a little bit different, so you want to be careful about interpreting that. This is not what we have. Now, because of this right here, I can think about if I multiply both sides by -1, I have -y equals x cubed. So what happened? Y changed to -y. If y is changing to -y, you're reflecting over the x-axis. Now again, the basic function here is my cube function, so think about that middle picture, y equals x cubed right here. What's going to happen to that if you reflect it over the x-axis? Well, this part is going to come down here, a mirror image here, and this part's going to be a mirror image here. So it's just going to flip over. And so your 0, 0 is going to stay the same, but you're going to go through 1, -1, and 2 will be -8, and -1 will be 1, and -2 will be +8. Your graph is just going to look like this. See, it's just this graph reflected over that x-axis. Sometimes I will sort of do a dotted line like that to indicate my reflection over that x-axis. But the key is just recognizing that that equation is sort of saying like y is changed to -y. Okay, well let's look at this one. Sketch the graph of the given equation by applying transformations to a standard graph. Y equals 1/2 times the square root of x plus 5. Now, let's analyze our equation here first. Notice I'm doing something to x before I do my square root. So that gives me a horizontal translation. If x plus 5 is equals 0, then x equals -5. I'm translating to the left, right? Okay. Now what's the 1/2 going to do? Since that's a fraction, it's going to cause a vertical compression of my graph. My points won't be quite as far away from that x-axis as they would be in the original graph. Now, let's do our mental picture for y equals square root x. Y equals square root x looks like that, doesn't it? What are we going to do to this graph? We're going to shift it left, so it'll be opening up over here somewhere, and then it will be compressed a little bit. Now, let's get our shift first of all. What used to happen at 0 now happens over here at -5. 1, 2, 3, 4, -5. Okay? Now, it used to 1, if I went over 1, I was on 1. But what's going to happen here? I should be only up 1/2 instead of 1. I'm going to locate over 1 from this new point. I'm going to go up 1/2, and let me show you what happens here. Notice your x value is -4. -4 plus 5 is a 1. The square root of 1 is 1. 1/2 times 1 is 1/2. So exactly that's what happened. Remember over here also, whenever x was 4, y was 2. So if from this point I go over 4 units, 1, 2, 3, 4, half of 2 is 1. I should only be on 1. Let's check that point out. If x is -1, -1 plus 5 is a 4. The square root of 4 is 2. Half of 2 is 1. And so you can see exactly what's happening here. We do have this graph shift to the left, but notice it has been compressed downward. Our points aren't rising up quite as fast as they did with that original square root function. Sketch the graph of the given equation by applying transformations to a standard graph. Now this one might be a little bit harder to recognize what that standard graph is, so let's look at our equation. We're doing something to x, and then we're doing what? We're squaring. Now if we weren't doing something to x, that'd just be x squared, wouldn't it? And then after we square, we're subtracting 3. Okay? My standard graph is y equals x squared. Okay? But we're going to do something to x before we square, and then after we square, we're going to do something else. Well, let's talk about what these things are doing. If I do something to x first, if x plus 2 is 0, x is -2. This says what? I have a shift to the left. And what does this do after the function? This is going to shift me down. So my y equals x squared graph should be shifted to the left and down. Now how far to the left? 2 units. How far down? 3 units. So this 0, 0 point should go to the left 2 and down 3. So over here I'm going to go over 2 and down 3 and put that point in there. Now, let me show you something here. With y equals x squared, from my little vertex point right here, if x is 1, y is 1. In other words, if I go over 1, I go up 1. So from here, my new point that I move that 0 to, I'm going to go over 1, up 1. And on the other side, it'd be the same. And notice if x is 2, y is 4. So from this point, I'm going to go over 2 and up to 4. Negative 2 also would give you a 4. I'm going to go ahead and sketch in these points, and then I want to show you something. The x value here is negative 1. Negative 1 plus 2 is a 1. 1 squared is 1. 1 minus 3 is negative 2. Notice where I am. Okay? Let's look at this point right here. My x is negative 2. Negative 2 plus 2 is what? 0. 0 squared is 0. Minus 3 is negative 3. This x value right here is negative 3. Negative 3 plus 2 is negative 1. If I square negative 1, I get 1. 1 minus 3 is negative 2, and you'll see that point right there. Do you see how that worked? All I needed to remember was that from this vertex, what does x squared do? It looks like this. 1, 1, 2, 4, negative 1, 1, negative 2, 4. If I remember those points, if I just shift my vertex over and then just do that same thing here, I have my new sketch. Now, I also want to show you this. Y equals x squared is symmetric to the y-axis. Notice when I shifted to the left and down, I'm going to put in a little sort of dotted line here. Notice my new graph still has symmetry, but the symmetry has been shifted over to the left 2 units. Okay? We'll talk more about this in our next lesson on quadratic functions. I have one other graph that I want us to look at in this lesson. Sketch the graph of the given equation by applying transformations to a standard graph. Now again, we've got several things going on here. I recognize my absolute value here, and I'm doing something to x before the absolute value, so I know I have a shift. Do you need to write that down to remember if you said x plus 3 equal to 0, then x will be negative 3. So I have a shift to the left 3 units. Okay. Now, I'm going to talk about this negative in a minute, and I've got this 2 here. I want you to notice that you could rewrite this equation, y equals minus the absolute value of x plus 3 plus 2. Okay? So what's that 2 doing? Notice that's like a plus 2 there. That's going to do what? That's going to shift us up 2 units. Have you recognized your basic standard graph? It's y equals absolute value of x, right? Mental picture, remember, is that V shape. Now, let's talk about that negative sign there, okay? Now, let's don't worry about this plus 2 right here. Is the negative with x? It's not, is it? It's not inside the absolute value where the x is. If that wasn't there, we could multiply both sides, couldn't we? Get negative y and get a positive here. The negative is with y, isn't it? Okay? So if the negative is with y, we're going to do what? Reflect over the x-axis. Reflect over the x-axis. Now let's do a little thing here. If I have this graph, what does it look like if I reflect it over the x-axis? It's going to look like that. It's going to be a V-shape downward, isn't it? And then remember, we're going to go left 3, up 2. Okay, so let's take this point, the origin point that's usually here. We're going to shift left 3 and up 2. And from that point right there, I'm expecting my graph to be a V downward. Okay? And since I don't have any multipliers, I'm going to go ahead and sketch this in. Remember, 1, 1, 2, 2. So if you come down, it's just going to be over 1 and 1. Let's look at some points here. Negative 3, 2. Notice up here, if x is negative 3, negative 3 plus 3 is 0. So I get y equals 2. So that point's correct, isn't it? Right here, x is negative 2, and I have a y value of 1. Let's check that. If x is negative 2, negative 2 plus 3 is 1. What's the absolute value of 1? It's 1. What's 2 subtract 1? It's 1, isn't it? Look at this one right here. When x is -1, -1 plus 3 is a 2. The absolute value of 2 is 2. 2 subtract 2 is 0. And so you can see that we do have the correct graph, but we didn't have to plot those points to sketch in the graph. All we had to recognize was the reflection and the shift, and then just repeat our basic graph. I hope that having looked at these examples, you get a better idea of how to look at an equation, recognize what the standard equation would be, whether it's the square function or the cube function or the absolute value function or the square root function, and then recognize, has there been a vertical shift? Has there been a horizontal shift? Has there been a reflection? Perhaps a compression? And then use those techniques to help you get a quick sketch of the graph. And then you can always rely on sort of checking yourself by choosing some of those x values and getting corresponding y values into the equation and seeing if you do have the correct graph. A lot of times this takes a little bit of practice initially, but once you sort of get the idea of what's going on here, it can really speed up your graphing skills and make doing graphs a lot easier than just doing that tedious idea of plotting points over and over and over. Thank you very much for looking at this lesson.